Hello.
Hi, Sayantan.
Hello.
Hi, Sorendu.
Hi, Bidango. Bidang, I'm connecting from my phone because there's something that goes wrong when I try to connect from my laptop.
Okay.
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 So several features I suppose will not be available.
Yeah, no problem. We will help you. If there are questions, will help you in knowing who are asking the questions.
So I see Bidang and Subhashish here.
Helen has also joined.
The speaker is Sayantan. Sayantan is here.
Yeah, I'm here.
Hi, Sayantan.
Hi, Sharon.
You're ready with your presentation?
Yeah, I will start sharing my screen then.
Yeah, why don't you start sharing your screen and I'll
Yeah.
over
Can you
your.
see my screen now? Or?
Yes. Yes. Yes.
Okay, so let me introduce the first speaker of this session, Sayantan Sharma. And this is a session on heavy ion physics, and Sayantan is the first speaker. He'll talk about recent theoretical developments on QCD matter at finite temperature and density. So Sayantan will start now, and you will be warned about time by the hosts. Okay. And before you start, I just want to remind the audience that it would be best, if you have questions, it would be best to wait until the end of the session. It would be best not to interrupt. Okay. In general, keep your mics on mute. If you have an urgent question, use the chat box. And at the first opportunity, one of us, either I as chair or one of the helpers, will pose that question to Sayantan. Otherwise, we'll save the questions for the end of the talk. Okay. And there I would request everyone who has a question to raise hands using the raise hand feature and not ask directly, ask only after you have the mic. Okay. So please put your mics off if you're not the speaker at this time. Sayantan, you have the floor.
Okay, thanks, Shurendu. I would like to thank the organizers for the DAE-HEP Symposium of this year for this kind of opportunity, and I will be discussing about the recent theoretical developments on QCD matter at finite temperature and density. So briefly, I would like to start by looking at the main theoretical challenges for QCD at finite density. So this figure in the left right shows the QCD phase diagram that is already very well known by many of you. However, I would like to stress out that most of the phase diagram is conjectured and it's not known very well from first principles. And we are trying to understand it both from theoretical as well as experimental side. So the beam energy scan program at RHIC is ongoing and it's trying to look at the this beam energy scan, which goes from all the way down to 7.7 GeV square root of S of the colliding nuclei. And this corresponds to a baryon chemical potential mu B by T of about 3. So this region between mu B of 2 to 3 times the temperature is the interesting region which will be probed by this program. And any analysis of the experimental data requires equation of state, which comes from first principles calculation, mainly from lattice QCD. And that is the most important wish list that we have for the beam energy scan program. There are many others. So secondly, we want to understand what is the curvature of the chiral crossover line that starts from mu b equal to 0, the vanishingly small baryon chemical potential, and goes all the way up to the finite density, so that we can understand how far or how close we are to the chemical freeze out line. And one of the important theoretical challenges is to understand whether there is a critical endpoint in the QCD phase diagram. And the other important aspect is to understand the relevant degrees of freedom. So in any phase transition, we want to understand what are the degrees of freedom when we go from one phase to the other. And in QCD, we know there is a crossover transition at small values of the baryon chemical potential up to some reasonable values of the baryon chemical potential. And we want to understand what are the relevant degrees of freedom. We know that it goes from a hadron gas to quark-gluon plasma phase, but then we want to understand the details of the hadronic interactions when we approach the crossover transition. So these are the wish lists that we want to address through the theoretical calculations, and I would try to address a few of these issues in my talk. So one of the most important theoretical techniques at our hand is the lattice QCD techniques, and they have been very much successful in giving us many first principles predictions about the phase diagram of QCD, especially at vanishingly small baryon density. We know that the phase transition is not a true phase transition but a crossover. But when we want to go and extend these lattice techniques at finite density, then the conventional Monte Carlo methods suffer from sign problem at finite density. There are different methods which allows to circumvent this problem. And currently there are two important methods. One which goes by the name of Taylor expansion, and the second is calculation done in imaginary chemical potential formalism, which allows us to go into the thermodynamic and continuum limits. So the main essence of the Taylor expansion is very simple. It involves expanding my physical observables around around the zero baryon chemical potential as a Taylor series in the baryon chemical potential normalized by the temperature.
The
So
lattice
for example,
lattice-
here I show.
ତାଙ୍କ paper lattice ରେ ହୁଏ ନା
Hello?
QCD ର
Sorry, was there any question or?
I would suggest no questions at this point. Sayantan, continue. If somebody doesn't have the
Okay.
speaker muted, they should mute the speaker now.
Okay, so here I show the expansion for the pressure as a function of the baryon chemical potential, and the first two coefficients are shown here explicitly. I refer to as a P2 and P4, and then the higher orders are called P6 and P8, and these variables I will use, and I will show the results for these coefficients in the next few slides. The interesting point is that many of these Taylor series have very important information. Like if you look at the Taylor series for the second order baryon number fluctuations, then they are expected to diverge at the critical endpoint. And of course, on a finite volume, there are no divergences, but then one can look at the ratios of higher order coefficients of the fluctuations, and they should be equal and independent of the volume, which will give us an idea about where, if we are approaching the critical endpoint. Now, in the most central heavy ion collisions, usually the system that is formed under experimental conditions have net strangeness to vanishingly small, and then usually for large nuclei, the ratio of the number of charges to the number of baryons is typically of the order of 0.4. So one needs to impose these constraints to mimic the conditions that are usually formed in the experiments. So if one imposes these conditions in the theoretical setup, it means that the corresponding chemical potentials are no longer independent, and one imposes non-trivial constraints on the chemical potentials corresponding to the strangeness and the charge. However, however, it's possible to vary these strangeness and the charge chemical potential by only varying the baryon chemical potential through these relations, which are also like Taylor expansions of these two chemical potentials. And below I show the results for the first order coefficients for the strangeness and the charge chemical potentials. So the leftmost plot is for the strangeness one, and for the middle panel we show the first order expansion coefficient for the charge chemical potential, and all of them are taken in the continuum limit given by this gray band. And they are tiny, but they are not negligibly small. So one needs to take into account these corrections very carefully. And in the rightmost panel, we show the coefficients of the third to the first order coefficient in the expansion of the strangeness chemical potential. And they are almost 10% of the this ratio is about 0.1. So indeed the higher order terms are much smaller than the leading order term. So once we know these coefficients in the Taylor expansion of the strangeness and the charge chemical potential, one can construct the full equation of state. So below I show the fourth order and the sixth order Taylor coefficients in the expansion of pressure under these conditions that the net strangeness is 0 and the net charge by baryon number is 0.4. And the gray bands are the continuum estimates for these quantities, and these black lines are the expectations from the hadron resonance gas model. So one can see clearly that as one approaches temperatures about 145 MeV or higher, then there is a clear deviation of the lattice data from the hadron resonance gas expectations. And for the sixth order coefficients, there are even more interesting features. First of all, the deviation occurs quite early, and then the coefficients become negative just above the chiral crossover transition temperature. And they may be remnant of more non-perturbative features. This sixth order coefficient going negative just above this chiral crossover temperature cannot be predicted within calculations from the hard thermal loop perturbation theory. So it's essential non-perturbative feature that can come out from the lattice studies. So these are the current lattice results for the equation of state at finite densities. As one can see clearly that in the region of interest near the chiral crossover region, the equation of state is now very well controlled for baryon chemical potentials about 2.5 times the temperature. And also in the rightmost panel, we show the results for the equation of state from two different groups using two different lattice discretizations, but they are all finally extrapolated to the continuum limit. And there is a very good agreement between two different group results, showing that these results are quite robust in the continuum limit. Now, the second point that I want to discuss here is what happens to the degrees of freedom when we approach the chiral crossover transition. So we are in a hadronic regime when we approach near the chiral crossover transition. Then we already saw in the expansion coefficients of the pressure that expectations from a naive non-interacting hadron resonance gas model already breaks down before we approach the chiral crossover transition temperature. And this is not surprising. In a strongly interacting medium, a quasi-particle description may not exist. Also, if the quasi-particle nature description is good, then of course one can mimic all the interactions in terms of a non-interacting gas of hadrons plus resonances. However, we already saw that with the lattice data having more and more precision, we can see that any naive or non-interacting hadron resonance gas description breaks down much below the chiral crossover transition temperature. So what are the reasons why the naive description of the hadrons in terms of a non-interacting gas of resonances and the hadron masses taken from a particle data book spectrum breaks down much below the crossover transition temperature? One of the first reasons is that the many baryon channels may not have resonant interactions. So there may be repulsive interactions which cannot be captured by mimicking it in terms of resonances. Secondly, recent lattice studies have shown that there can be non-trivial in-medium modification of baryon masses. So here in this figure, the solid points or the circles, they denote the negative parity baryons in different strangeness sectors. In all these strangeness sectors, one can see that the negative parity baryons have a very different mass, in medium mass, than the positive parity baryons shown by this open symbols. And they become degenerate only when the chiral symmetry is almost restored near the chiral crossover transition. Moreover, the resonances may have thermal widths, and they may significantly contribute to the thermodynamics. So here, the results for comparison between two different hadron resonance gas models are given for different strange baryon sectors. So So the red line is the naive hadron resonance gas prediction, taking into account only resonances and the hadrons from the particle data booklet. And the yellow bands are those when the resonances are considered keeping into mind their thermal widths. And one can see that in higher strangeness sector, the lattice data given by the black points are consistent with the hadron resonance gas models, where the resonances are taken into account, where the resonances are thermal modifications are taken into account. Indeed, when we look at higher order baryon number fluctuations, they are more sensitive to this departure from the naive hadron resonance gas model, including only the hadrons from the particle data booklet. So here, these points are the lattice data for the fourth order baryon number fluctuations, and these the black line is the prediction from the hadron resonance gas model, taking into account only the experimentally known states. However, from lattice studies and different quark models, one knows that there are many more resonances which have masses below 2.5 GeV. If one takes into account those, then one can get a prediction which is given by this red solid line, which is called the quark model enhanced HRG predictions. However, we can see that though the quark model predictions agree well with the lattice data for lower temperatures, again there is a slight departure. And then this departure can be taken into account by taking into interactions, repulsive baryon interactions, given by this red dashed line in the mean field approximation. So the summary is that lattice data, especially from the higher order fluctuations, they are becoming precise enough, and they are allowing us to understand about what is the description, hadronic description in this temperature range below the chiral crossover transition. So at present, it seems like, of course, additional resonances and hadrons from the quark models are necessary, and also one needs to consider repulsive baryon interactions. However, everything is not yet settled. So if one looks at different thermodynamic observables, like for example, in the left panel, the ratio of the fourth to the second order baryon number fluctuation is shown. So one can include, of course, the repulsive baryon interactions by doing excluded volume analysis, and this is given by this magenta lines. So clearly, this ratio of the fourth to the second order baryon number fluctuation data, this gray band which comes from the lattice continuum extrapolation, they clearly support the need for an excluded volume analysis of the naive hadron resonance gas predictions. However, there are still a few more ratios, like one shown in the right panel of this figures. So, for example, if one looks at the correlation between baryon number and charge, quantum numbers normalized by the second order charge fluctuations, then it is not yet clear which of these type of descriptions in terms of hadron resonance gas and including interactions will describe the lattice data. So having more and more precise lattice data and looking at different such observables will allow us to constrain the effective description, hadronic description below the chiral crossover transition. Currently, none of these models can perfectly describe the QCD data at freeze-out. And here I discuss further about cross correlations. So these are the higher order cross correlations between baryon number and strangeness, normalized by the fourth order fluctuation, strangeness fluctuations. And as we can see that the lattice data, which are shown by this data points, clearly deviate from the naive hadron resonance gas description of just taking into account the experimentally known hadron states. So one needs to augment it by the quark model states. However, there is a similar effect here. So at low temperatures, quark model description is good, but then at some point it breaks down. So then one needs to take into account the repulsive baryon interactions. Off-diagonal fluctuations are thus more sensitive to the deviation from the naive hadron resonance gas model, and it can constrain all these kind of hadronic descriptions much better. One can also look at specifically the strangeness sector, because it is very well known that the strangeness 2 and the strangeness 3 baryon sector may have many more resonances which are not yet experimentally all observed. So if one looks at this specific observable, which usually which zooms into the contribution of the higher strange baryons, like the strange 2 and the strangeness 3 baryons, and one can see that the lattice data given by the symbols, open symbols, they clearly favor the presence of these excited states in the multi-strange baryon sectors. So yeah, for the strangeness sector, it's very important that one takes into account all these higher resonances, especially in the multi-strange baryon sector. So now I switch gear into understanding our current understanding on the curvature of the chiral crossover line. So in QCD, of course, all the quark masses are finite. However, the U and the D quark masses are much lighter than the intrinsic scale of QCD. So the SU2 left cross the SU2 right is nearly an exact symmetry, even for QCD with 2 + 1 flavors. So one can look at different chiral observables, their derivatives, and then one can get a transition temperature, though the phase transition is not a pure exact phase transition for QCD with physical quark masses. However, it makes sense to talk about a very precise crossover transition temperature, which has been measured recently. And it, sorry, here the units are missing. So it is 156 plus minus 1.5 MeV. And this is now very well constrained in the continuum with an error of about 1%. So when one knows this chiral crossover transition temperature at vanishingly small baryon chemical potentials, then one can calculate the temperature as a function of the different chemical potentials as a series given by the first equation. So if one looks at the chiral crossover line in the temperature and baryon chemical potential axis, then these expansion will be in terms of the baryon chemical potential, and we will get the curvatures kappa 2 and kappa 4, which are the Taylor expansions of this curve. So we have results for this strangeness neutral system. It gives a kappa 2 in the continuum limit from using a particular discretization of fermions, which is like 0.012, and using different fermion discretizations and very different technique, one also gets this curvature to be in the same order of magnitude. So here, this is a summary plot. So all these different points in the right corresponds to the kappa 2 measurement using different fermion discretizations and different techniques. So they are all consistent with each other now. because every result is now taken in the, especially these final 3 results in the top, they are taken in the continuum limit. And currently the kappa 4 is consistent with 0 with quite large error bars. So when one knows these curvature coefficients, then one can draw this crossover line. So in the figure, this blue and the dark dotted line, they corresponds to the crossover line when the energy density and the entropy density is kept fixed. And these different lines of constant physics, they agree within about 2 MeV for baryon chemical potentials by temperature ratio of order of 2. So this expansion up to order mu b to the power 4 is consistent for these values of the baryon chemical potentials shown here. The yellow line is the crossover line, that is the line that is determined using the curvature coefficients, and these magenta points are the calculation of the freeze-out curve from the star data, and the red point here is the analogous calculation from the Alice data. So so the star data looks that it falls much deeply, but there's a good agreement between the star data and the lattice measurements, at least for larger values of mu b. And of course, at vanishingly small baryon densities, the Alice data agrees very well with the lattice QCD crossover transition temperature and the freeze-out temperature that was calculated from the Alice measurements. So now moving on to the critical endpoint search and its status from the lattice studies. So just to briefly remind the main methodology that is used. So one looks at the Taylor series of the baryon number fluctuation, and if one looks at the Taylor series, then the series usually diverges if it has a singularity or a critical endpoint. And if the singularity is in the real baryon chemical potential plane, then of course all these higher order fluctuations which come as a Taylor coefficient for when this second order baryon number fluctuation is expanded as a Taylor series, and all these coefficients should be positive. And hence the radius of convergence of this series will determine the location of the critical endpoint. And formally, the definition goes as in the following way. So here, of course, one has to take the ratios of the different baryon number fluctuations if one wants to get the estimator at the order n. And strictly for defining radius of convergence, one needs to go to very large values of n. So one needs to understand how large is this n that one needs to go to get a reliable estimate of the radius of convergence. And of course, when one goes to higher and higher values of this n, then one needs to calculate higher order baryon number fluctuations. And the signal to noise ratio for these observables deteriorates very rapidly as a function of n. So these are the results shown for the higher order different baryon number fluctuations. So in the leftmost part of the figure, leftmost part of the slide, one shows the 6th order baryon number fluctuations and the 8th order baryon number fluctuations from the hot QCD collaboration. So these are not continuum extrapolated, but one can see that especially for the 8th order baryon number fluctuation, it's negative at temperatures above 135 MeV. And similar trends are also visible from results from a different lattice group in whose results are summarized in the right part of the slides. So one can see that the sixth order barrier number fluctuations start showing a dip at temperatures already above 135, which means that its derivative, which is the eighth order fluctuation, should be negative at those temperatures. So clearly, if one of these higher order coefficients are negative, then the critical endpoint cannot exist in the real baryon chemical potential plane for those values. This allows us to constrain the temperature of the critical endpoint. So it seems like if it exists, it should exist at temperature below 135 MeV. So this slide shows the summary plot from all different lattice groups, the current status of the critical endpoint search. So, this yellow region is the disallowed region that comes out from studies of different estimators. Clearly, these results come from results from the hot QCD collaboration. Clearly, if one has a temperature, if one zooms into this temperature range where one expects the all these higher order fluctuations to be positive, then it seems like that the baryon chemical potential should be larger than 2.5. There are other lattice results from the imaginary chemical potential analysis, which is shown in this as these green points, and they are consistent with the bound shown here. There are a few more lattice results which are a bit below, but I would like to remind here that all of these lattice results are not in the continuum limit. So if one takes the continuum limit and systematics properly into account, then everything should agree. And currently, we do not have a final answer on this, on the location of the critical endpoint. So I will skip this slide. So currently, it seems like with the current precision from the lattice, it seems like the higher order curvature coefficients are consistent with 0. So the dominating contribution comes from the second order coefficient, curvature coefficient. So from there, this current constraint exists. However, if the higher order curvature coefficients of this chiral crossover line is determined with a good precision, and one can reduce the errors on this, then even if this fourth order coefficient is 10% of the second order curvature coefficient, then it will start to significantly contribute to the curvature of the crossover line, and it will bring down this chiral crossover curve even to higher values of baryon chemical potential. So one would need to go to higher and higher order cumulants to get any radius of to get to the critical endpoint, because ultimately this crossover line should at some point end at the critical endpoint. So the more curved it is, the more higher orders we need to go to get any bounds on the critical endpoint.
Sayantan, are you?
So finally, I would, yes.
Are you more or less done? Because you have only 5 minutes.
How much time I have left?
0, basically.
Yeah, I'm almost done. Yeah. Okay, so I would. Can I take 2 minutes more, because I think I started 2 minutes later. So okay, I will just quickly go through it. So in equilibrium thermodynamics, of course, one measures fluctuations of globally conserved quantum numbers like baryon number, electric charge, and strangeness. However, in the experiments, one measured hadron multiplicities within a certain rapidity window. So it's not a conserved number. And there are effects like feed down corrections from resonances, they may push some of these hadron multiplicities out of this resonance windows. So it is important to understand whether how much information does it have and whether they tell us anything about the fireball, whether thermal equilibration is achieved. So recently there has been a lot of interesting studies on this topic. So like looking at the variance to mean for net charge and net protons are not enough, because those ratios are very sensitive to this resonance decays, and then they move the observables out of the rapidity window. So there are proposals to look at new different ratios which are not so much sensitive to this resonance decays. And here I show the plots of the analysis. So calculating the phase out temperature and the chemical potential from taking into account all these new ratios, and also and fitting it to the thermal model expectations, shows that for collision energies of 19.6 GeV and above, it seems like one gets a common phase out temperature and chemical potential for different observables from different analysis of different moments. And it starts to break down at lower square root s, but it seems like thermalization is observed because so many different moments give same temperature and the band chemical potential. Of course, there are studies looking into the thermal statistical hydronization model by looking into only statistically independent particle yield ratios. And yeah, and they see similar trends. And recently, I would like to tell that there are thermal fits to the hadron yields and central lead-lead collisions at LHC, which has been taken into account considering these additional quark model states. And they observe a strong influence from resonances from in the isospin half and 3/2 channels. And if one takes into account corrections due to the pionuclear interactions, then one gets a freeze out temperature of 156 MeV, which is consistent with the earlier analysis. Okay, I cannot cover all this, but I would like to also in the passing mention that it's important to look at also higher order ratios of higher order cumulants. So one such proposal is to look at this ratio R51, which is the ratio of the fifth order baryon number fluctuations to the baryon number density. And these observables should have lower systematic errors, and also in the lattice it's much within the current precision we have. So it will allow for a good determination. Already one can see that for this ratio R62 for the proton number fluctuations at 54.4 GeV, one sees that this high statistics star data is already consistent with the lattice predictions given by these bands. Okay, so I end with this outlook, and I will not go through it, and I will.
Thank you, Sayantan.
Open
Can you stop
questions.
sharing, please? Can you stop sharing the screen?
Yeah, sure.
Yeah. Unfortunately, you have exhausted time for questions. I'll ask Andrea to set up by sharing his screen. Meanwhile, I can take one question if there's anything urgent. Is there any question? No. Okay, Sayantan, thank you very much. Andrea, can you set up your...
Yes, hello.
Yes.
Good Good afternoon, good evening, everyone. So let me try to share.
So Andrea Dainese will now talk about results from the LHC Heavy Ion program. I'll warn you 5 minutes before the end. If there are questions, we'll take it at the end. Please do not ask questions in between. Thank you. Andrea, you have this floor.
Okay, thank you. So please let me know if anything is wrong with the connection or the sharing. I'm delighted to give here this overview of recent results from the LHC Heavy Ion program. I thank the organizers. And of course, it's a pity that we have to meet only virtually. I look forward to visiting India soon after the pandemic is over. So I don't have to say too much for the introduction after the very nice presentation that just ended. So I will just say that with heavy ion collisions, we explored the confined phase of QCD matter, the QGP, and in particular at the LHC, where we collide lead-lead, we reach a large energy density, more than 15 GeV per Fermi cube, over a large volume that is of the order of 5 to 10,000 Fermi cube. So we explore this region of the QCD phase diagram at very small biochemical potential at the LHC, and the system follows a similar path as the one followed by the early universe. Now, I don't have to say too much on the evolution of the collision. I like to show this nice animation to say that at the beginning we have a QGP, a high temperature state, and then it expands, it strongly expands longitudinally, but also radially, and finally freezes out and hydronizes. So this is now on a timeline, a few of the phases of the collision, and I will use this timeline to present a few recent results from the LHC experiments that provide information on the system in various phases of its evolution. So you see the system lives for about 10 Fermi over C. Now, what we can learn by studying the collisions at the LHC is about, of course, several aspects, starting from the initial stage, then macroscopic properties of the system. We can explore color deconfinement and its consequences. We can study parton interactions in the QGP, and we can study its characteristics as a high temperature medium in terms of viscosity and expansion dynamics. So here you see nice event displays from the latest lead-lead run at the LHC in run 2. So here I list in blue the colliding systems. Of course, lead-lead at 2 collision energies. We also had a very short xenon-xenon run, which however proved quite useful, and extended proton lead running, in addition, of course, to PP reference data. Now, starting with the initial state, I will show one result essentially from ultra-peripheral lead-lead collisions. So in ultra-peripheral collisions, the lead nuclei don't interact hadronically, but they interact via the electromagnetic field that they produce. So the electromagnetic field, and in particular the photons that are associated to it, can interact coherently with the gluon field of the nucleus, forming, for example, vector mesons like the J-psi, and providing information on the gluon field itself. So on this, I show one recent result from Alice on coherent J-psi production in ultra-peripheral lead-lead collisions. And so this is the cross-section as a function of pseudo rapidity, and we see that it is described by models that incorporate a strong gluon shadowing, so a strong reduction of the gluon PDFs at low q square in this case, and small Bjorken x smaller than 10 to the minus 2. So this is a prominent feature of the initial state that we see. And now let me make a quick detour with ultra-peripheral LED collisions. We can also use the LHC as a photon-photon collider. The so-called light-by-light scattering processes are shown here. So here on the left, you see the standard model Feynman diagram, and in the middle, you see a possible new physics Feynman diagram in which the photons couple via, in this case, an axion-like particle. So CMS and Atlas have made measurements, and here I show from a recent Atlas paper their results, and you see that these measurements from LED provide the stronger constraints on the coupling of axion-like particles in a range of mass that is quite broad, between 10 and 100 GeV. So this is extremely interesting. Now, moving on, another way to study the initial state is to look at the production of probes that are produced in the system, and their production is affected by a possible modification of the initial state. And then they are traversing the QGP without interacting, so they are kind of QGP blind. And there we can use, for example, the nuclear modification factor that compares the yields in lead-lead to those in proton-proton collisions, scaled by a geometrical factor, number of binary collisions. So there, one of the main such objects is the Z to mu decay, where the muons from the Z don't interact with the QGP. So at variance with the J psi that I showed before, this probes high Q square and also equally small x. So this is a measurement on the left by Alice of the Z nuclear modification factor as a function of rapidity, and we see a trend of decreasing RAA when we go to lower Bjorken x, so higher rapidity, which is consistent with nuclear PDF shadowing, this time at much larger Q square of the order of course, the square of the Z mass. And we have also LHCb contributing in this area. These are measurements in P-LED and LED-P collisions of the Z cross-section, also compared with calculations that include or not nuclear shadowing. Now, moving on, when we have after the collision, the first phases, the system is characterized by huge angular momentum, as you see illustrated in this sketch, that is of the order of 10 to the 21 revolutions per second. Of course, these are order of magnitude estimates, and also huge magnetic field of the order of 10 to the 14 Tesla. So these are two, let's say, global properties of the system that we started very recently to probe. The large angular momentum we probe via the so-called spin alignment of vector mesons. So essentially this angular momentum is transferred to the quarks via spin orbit interactions. So it polarizes quarks. And then if quarks recombine to produce vector mesons that have spin 1, a spin alignment could appear. And indeed here we see a recent result from the Alice collaboration in which a deviation of the K-star measurement for this ρ00 parameter from 1/3, which is what is observed in PP collisions. So this deviation that is marked in red indicates a spin alignment in lead-lead collisions. Another way to probe this initial effects, and now considering the magnetic field, is to look at the charge-dependent particle emission anisotropies with respect to the collision plane. So this is also a recent measurement by the ALICE collaboration, which studied these observables for charged particles here on the left and for D mesons on the right. Now, D mesons contain C quarks, and C quarks form very early in the collision due to their large mass. They can only form in unscattering processes. So they really probe the magnetic field in the initial phase when it is highest, and then it goes down quickly. And here we see in this slope, which is a difference of this directed flow for particles containing a C quark with a positive electric charge minus that of particles containing a C quark with negative electric charge. We see a slope that is not fully significant. This is 2.5 sigma, but it is an interesting hint of the effect of this magnetic field. So this is definitely an area that will profit a lot from the high precision of the future runs. Now, going forward and starting to look at measurements that are sensitive to the QGP directly, I start with quarkonium studies, where one probes at the LHC the interplay of dissociation and regeneration. So Q-cube pairs can dissociate because of color screening, depending on the quarkonium binding energy. And on the other hand, the high charm quark density can lead to additional charmonium formation, the so-called regeneration. So let's look at recent data. I start with botonium measurements, in this case by the CMS experiment. So here you see on the left a plot that has become quite iconic, which shows the upsilon family, 1s, 2s, 3s, which has a decreasing binding energy, as you see here on top. And by comparing to proton-proton, which is the red dashed line, we can see even by eye the sequential suppression. So the higher states are more suppressed than the 1s. And this is now quantified here in this other plot in the nuclear modification factor as a function of collision centrality from peripheral. And in central, we see the maximum suppression, and it is again ordered according to the binding energy. So this is consistent with sequential suppression, and of course it carries in principle information on the temperature of the medium. Now, when we look instead at the lower mass quarkonium states, the charmonia, we have this interesting interplay between suppression and regeneration that I just discussed. And here this ALICE result of the nuclear modification factor of J-psi shows quite clearly the physics at play. So here at high PT, we have suppression that is consistent with the color screening. But then when we go to low PT, we see the suppression is lifted, and this is consistent with an additional source of J-psi from the regeneration of CC bar pairs. And we also see that when we go from forward rapidity to central rapidity, where we have more charm pairs, then this effect is larger. Now, moving still a bit forward, but staying still in the initial phases, we can study the interaction of hard partons with the QGP using jets and explore the phenomenology of parton energy loss. So hard quarks and gluons are produced initially, and then they interact strongly with the QGP. And jets lose energy and also are modified in their fragmentation pattern by induced gluon radiation, as you see in this sketch here. So a first measurement that one carries out, and here you see a compilation with results of ALICE, ATLAS, and CMS is the inclusive suppression of the yields of jets, so still this nuclear modification factor that led over PP, now for fully reconstructed jets. And we see that the LHC experiments nicely complement covering a range that goes from 50 to GeV to 1 TeV, and we see a suppression of the yields by a factor 2 to 4. So this means that energy loss brings energy outside the jet cone, and the jet finders algorithms then do not find the corresponding jet. This is depicted in this sketch. So it suggests that gluon emission induced by the QGP is producing particles at large angle and also low momentum. Those also escape the jet finding. Now we see that this evolves with centrality. Here is a measurement by ATLAS. In most central collisions, here in purple, we have maximum suppression, and then it is gradually reduced as we go towards more peripheral collisions. Now, to understand more in detail the pattern, differential studies are carried out, and there something that is extremely useful is to use Z-jet recoil measurements. So you have a jet that is recoiling against a Z boson. So the Z boson essentially estimates the initial parton energy, the energy of the parton that originates the jet, and then you can essentially have a very clean measurement of the fragmentation function of the jet. So here you see plotted the PT of tracks in the jet in lead over PP for jets recoiling from a Z boson with PT larger than 30 GeV in central collisions. So we see that this PT distribution exhibits a suppression at high PT and an increase at low PT. So gluon radiation induces an increase of partons in the jet fragmentation at low PT. Now, to study even more how the medium responds to excitation by jets, the LHC experiments have started a broad campaign of substructure measurements. So here I show one example by the ALICE collaboration of a study that used the so-called grooming technique. So essentially, it goes back in the jet history from the final state particles to find the first hard splitting, and then this can be compared, the angular distribution of this first hard splitting can be compared between lead-lead and PP collisions. And what is found qualitatively is that the jet core is more collimated in lead-lead than in PP. This you see here. So at large angle, there is a suppression in lead-lead, and at small angle, there is an indication for an increase. So this is a consequence of how jets react to interaction with the medium. Now, another interesting feature of energy loss that has been predicted since many years, way before the LHC started, is the mass dependence of energy loss. So at the LHC, one can study that already with separate measurement for C and B quarks. And of course, these measurements are still quite limited in precision, but we already see, for example, in these CMS measurements, an indication that B mesons and also D mesons from B meson decays are less suppressed than prompt D mesons. Here they are shown in green, and this is what is expected as a consequence of the so-called dead cone effect, which reduces gluon radiation for high mass quarks. So essentially, you have that radiation at small angles is is suppressed. Now, I mentioned C and B quarks, so experiments are going even heavier, and we have from this year the first observation of top quark production in lead-lead collisions by CMS. You see an extremely nice event display, and here the cross-section measured and compared with the calculation. So this proves the excellent, the superb quality of the detectors. Even in lead, one can reconstruct such complicated topologies. The physics case, when much larger luminosity will be available, concerns accessing the time dependence of jet quenching using time delay from boosted top decay topologies. So you have this chain top to W to jets. And this was proposed in this theory paper. Now, moving still a bit forward, we go to the expansion of the system, and it is of course well known that the system behaves like a fluid, like a liquid, and that its expansion is very well described by hydrodynamic calculations. So there, what one observes is this expansion in terms of flow. So here you see measurements by the ALICE collaboration of spectra, for example, of pions and protons here in PT from peripheral to central collisions. And what one sees is that the maximum of this spectra shifts to higher values of PT when going to central collisions, and even more for the protons. And this is consistent with the fact that hadrons are carried in the expansion by a common velocity field, which imparts to them an additional momentum which is proportional, to their mass. Now, a phenomenological driven fit of this spectra with the so-called blast wave parametrization allows to have an estimate of the expansion velocity, this beta t, which you see reaches 65% of the speed of light in central collisions, and also of the kinetic freeze-out temperature, that tells us at which temperature hadrons freeze out and cease to interact elastically. Now, when studying the expansion of the system, it is very convenient to use non-central collisions and to exploit the built-in elongated shape of these collisions. As you see, when two spherical nuclei collide non-centrally, then the system that they form is elliptical. So then, as a consequence of the expansion, this leads to an azimuthal modulation of particle production if measured at given momentum. So then and this is described in terms of Fourier harmonics. So when measured as a function of transverse momentum, the dominant element of this azimuthal modulation, which represents the elliptical shape, is called elliptic flow V2. And you see it shown in a recent measurement by the ALICE collaboration for 6 different hadron species here on the left, which have, of course, different quark content and different mass. And this nicely shows 2 prominent features. So at low transverse momentum, this pattern is ordered in mass, and this is a consequence of the radial flow that I described previously, while at intermediate transverse momentum, it is particles tend to group in a group with baryons and a group with mesons. And this suggests that for this momentum range, the flow is imparted at parton level, and then it is transferred to hadrons via a mechanism recombination of quarks from the system to form hadrons. Now, recently, the ALICE collaboration extended these measurements even to light nuclei, as you see here, deuteron and helium-3. And also for these, you see that they follow the mass ordering at low transverse momentum. These data are the basis for theoretical works that recently have started to combine measurements of spectra and flow coefficients from also more than one experiment at the LHC. Here you see ALICE and CMS carry out a sophisticated Bayesian analysis and fit essentially the properties of the hydrodynamically expanding medium. So here I show just one example, the QGP shear viscosity versus temperature. So the shear viscosity, of course, is a characterizing quantity for a fluid. And it shows that the quark-gluon plasma is the fluid with the lowest viscosity. It is 10 times less viscous than any other form of matter. And the precision that is reached is now of the order of 20% on the measurement of this property. Now we have at the LHC recently started to measure these flow coefficients, let's say also for heavy quarks. Here you see recent compilation of measurements by the ALICE collaboration that compare the elliptic flow coefficient of pions here in white, and then d mesons in orange, J psi in red. There are also electrons from BDK and even the upsilon. So we see that all these particles exhibit flow except for the upsilon. At intermediate PT, there is an ordering in the V2 value of J psi d and pions, which is consistent with the contribution of recombination. The model description that I do not show here shows that suggests that C quarks have a thermalization time of 3 to 8 Fermi over C, which is of the order or smaller than the QGP lifetime, so they may reach thermalization. We also can conclude that B quarks participate in the flow of the system, while the very heavy upsilon 1s doesn't exhibit significant flow, which could be consistent with both its large mass, so the flow, if any, would appear at very large momentum, and also the small BB bar recombination due to the small beauty cross-section, of course. Now, let me connect, starting from the flow measurements, to one of the most surprising findings at the LHC. I would say this is probably one of the few unexpected findings, which is the observation of collective effects in PP and PLED collisions. So here I show that the experiments measure this flow, so this V2. Also, in this case, it is for proton-proton collisions. These are results by the CMS collaboration, where you see these are collisions with a very high final state multiplicity, and there is a finite flow for several hadron species, with also an indication for the same mass ordering that is seen in lead-lead. So we said that this is high multiplicity, so what is done usually is to compare different colliding systems, PP, PLED, xenon-xenon, and lead-lead, as a function of charged particle multiplicity. And here you see from ALICE this elliptic flow now for all charged particles. And what is seen is that the value of the elliptic flow is similar in all colliding systems at the same particle multiplicity. There is, of course, a higher flow in lead-lead, but this is understood in terms of the higher initial ellipticity of the system that is, of course, not there, or to a much smaller extent in PP and P-lead collisions, where essentially it is not given by macroscopic geometry, but fluctuations of the parton densities in the initial state. Now, another aspect of this surprise involves hydrochemistry. So what is seen is that if you compare the yields of various particle types, in particular the strange hadrons, to that of pions, and you look as a function of multiplicity for different colliding systems, all data line up on the same continuous pattern that is found to be the same for different colliding systems within uncertainties, of course, and also independent of center of mass energy. So this suggests that also in the hydrochemistry, in how quark flavors are distributed in particles, there may be a similar underlying physics mechanisms in different colliding systems that somehow switches on gradually in PP and P-lead collisions as you increase the multiplicity, so the activity of the event, and then slowly leads to the values observed in heavy ion collisions, which are attributed to the formation of QGP.
You have 5 minutes before.
Okay, thank you. So a big question that is on the table is whether this suggests that the mechanisms that microscopically lead to thermalization and formation of QGP are the same that start gradually to be present also in small collision systems when you go to high multiplicity, essentially due to overlap of color states in the final state of the collision. So yes, this is now a big question on the table. Is a QGP formed in PP and P-lead collisions? So experiments at the LHC have been looking also for another characteristic signature of the QGP in lead-lead, which is energy loss. So do we have energy loss in PP and P-lead? And if we look at the nuclear modification factor, this is a compilation of Atlas and Alice measurements. This is fully consistent with unity. So there is no indication of energy loss, which in uncertainties. And what is interesting is that, however, you find that the elliptic flow of particles in jets in P-lead collisions is larger than 0. You see these red points up to high momentum, transverse momentum in P-lead. And in lead-lead, this is interpreted as energy loss in an azimutally asymmetric medium. So this may be consistent with the final state interactions, but when we look at the yields, we don't see them. Maybe it could be that the effect induced is too small. So high precision measurements in run 3 also will try to address this open question. Is there no QGP, or is it too small geometrically to induce energy loss? So this brings me to the future that I will cover quickly. Here I show the present assessment of the LHC schedule. Of course, these times schedules may still change. So in run 3 and run 4, the main goal is to collect a very large lead-lead sample, 13 inverse nanobarn at the LHC per experiment, essentially Atlas, CMS, and Alice, and a bit less for LHCb. And this will give a factor 5 to 10 integrated luminosity for rare triggers with respect to run 2, sorry, and a factor 100 for the minimum bias sample for the upgraded Alice detector. The interesting open questions in the small system sector that I show also prompted to propose a very extended small systems program with extended PLED running, proton-proton running with low pile-up with focus on high multiplicity studies, and also a short oxygen-oxygen run may be scheduled in run 3. This was discussed in detail in a workshop a couple of years ago, and the findings were then setting the basis for the future program. Now the experiments will be all upgraded. Alice is undergoing a major upgrade in this long shutdown 2, already for run 3. It will have 3 times better tracking precision, continuous readout at 50 kilohertz, and further upgrades are in preparation for run 4, in particular for the tracker and a forward calorimeter for photons. LHCb is also being upgraded now in LS2, and its upgrades will give access to lead-lead collisions, probably not yet up to central collisions. That is the goal instead of the future upgrade of run 5, which of course is designed also for the flavor program of the LHCb, but this is an interesting benefit for heavy ion running. Atlas and CMS instead will have their major upgrade in run 4, and here I indicate the main impact for heavy ions, the extension of the tracker acceptance up to 8 units, and cap calorimeters, and maybe most interestingly, the precise timing detectors for pile-up rejection in PP will enable PID measurements using time-of-flight techniques. Now, something that is also in discussion is to extend the heavy ion program at the LHC into the 2030s, so run 5 and 6. And they are using ions lighter than lead, like krypton or argon, would give a large increase in equivalent luminosity and open the access to very rare probes that that now are just starting to be explored, like the top that I showed, the Z-Jet, heavy flavor baryons with more than 1 heavy quarks, and so on. And exactly to that target, the ALICE collaboration is now conceiving a proposal for a silicon-only heavy ion experiment for LHC run 5. It is documented here, which would have as the main goal to achieve the ultimate performance for multi-heavy flavor, thermal radiation, and soft hadrons, so nicely complementing the hard probes capabilities that Atlas and CMS will, of course, retain in run 5. So with that, I come to the summary. I hope I managed to give you an idea of the large scientific output that we have from the run 2 campaigns. We have detailed insight of the QGP workings and properties, and the LHC data have opened a new research direction on the emergence of collective effects from PP to heavy ions. We are heading towards precision measurements in runs 3 and 4 with much larger samples and better detectors, and there are strong opportunities from the extension to run 5 with lighter nuclei and frontier detector technology. And with that, I thank very much you for your attention, and once again the organizers.
We are kind of short of time, but I'll take 2 questions. At the end of the session, I propose to have questions to all the speakers in case there are extra questions. Okay, so I would ask all the speakers to stay on till after the session. So anyway, right now, the first question I saw in the queue was from Rohini. So Rohini.
Thank you very much for this really wonderful talk. But I had 3 questions, but let me finish again.
I'm afraid I cannot
hear
you.
Can't hear Rohini. If Rohini can fix the speaker, then we can come back to her. The second question goes to Rajiv Gawai.
So can you go to slide, please?
Hello. Can you
Hello.
please
Yes.
go back to your slide on the flow results?
This one?
Yes. My question was on your left side. In the RHIC results, there was something called constituent scaling, which was seen. Is something
Yes.
like that visible here, or there is? What is the comment on that?
Yeah, so this was tested. So that is tested by plotting the V2 divided by the number of quarks, so 2 or 3 quarks for mesons and baryons, as a function of PT, also divided by the same quantity. So that worked very well at RHIC. At the LHC, it doesn't work that well, so it works to the level of 20%. So this has been tested, and it was something that was suggested by, let's say, a simple picture of recombination, formation of hadrons by recombination. But it seems that at the LHC, the situation may be a bit different than that. So maybe because the flow is still strong in the hadronic phase, and then it still modifies the dynamics of particles when hadrons are already formed. This could be one possibility.
Okay.
Okay.
Rohini, can you speak?
Yeah, can you hear me now?
Yes.
Yes, very well.
Okay, thank you very much. I had two questions. One was for your slide 30, which was one of the most interesting things for an outsider about something that is not expected. But I had a question because you had various lines in the right-hand plot.
Sorry, 13 or 30?
30.
Okay.
This was your similarity between PP, PB, all PP and PPB.
Yes.
Yeah, so 30. Yeah, here. I was just curious, can you tell us more about the various lines, what they are on the right-hand side plot? That is what I wanted to know.
So this calculation that is shown here as a band with various patterns and that you see for all colliding systems is essentially a hydrodynamic calculation. So this assumes the formation of a high density medium in all systems. And then it assumes the fact that the flow is induced by expansion of the medium according to hydrodynamics, and then hadronic phase rescattering. While instead, this PTA comparison that you see only in PP, and which describes to some extent the data, but not fully, this doesn't include a medium, but essentially there is a superposition of color strings that induce in the final state via microscopic interaction an effect that mimics the expansion, the collective expansion. So this is the so-called color recombination scheme that is in PTA.
Okay, thanks.
So this can also provide a qualitative description of the data.
Okay, that's very interesting.
Rohini, can I interrupt you here?
Yeah.
We will come back for further questions at the end of the session.
Okay,
and
okay.
Out of time, I would like to request to thank Andrea for the talk and move on to the next talk. Andrea, can you stop sharing the screen? Yeah, thanks. Helen, if you're ready to start, can you start sharing the screen?
So hopefully you can see my screen and my slides and hear me now.
Yes, it's visible. Thanks.
Okay, so again, I would also like to thank the organizers for inviting me to talk. It's always fun to give these discussions, and I'm here to talk to you today about the latest results from heavy ion collisions at RHIC It's nice to be last in the series because Andrea and Sayanta have set me up. So hopefully I can dive right in. So 2020, we're celebrating this year 20 years of RHIC running, and you'll hopefully see by the end of the talk that I have many exciting things that we are coming out with today. So over these 20 years of RHIC running, the versatility of the accelerator has really come into play. And what you see here on the x-axis is the range of square root S, so the beam energies that we've collided, going from 200 GeV, which is our top energy, all the way down to 7 GeV at the very lowest energies in our so-called beam energy scan that you also heard talked about during the theory discussion. And also the variety of beam species from, we have a very strong spin program, a cold QCD program. So we have PP, P aluminium, P gold, D gold, helium 3 gold, copper, copper, copper gold, the 2 isobars, zirconium and ruthenium, gold, gold, and uranium, uranium. So you see, we've really sort of been able to explore the phase space of what we can make with QCD matter. And it's still evolving today, and you'll hear very briefly at the end of my talk about the STAR Forward Physics Program and the S-Phoenix detector, which are both about to come online. So what does the versatility of RHIC means? So you just heard from Andrea that if you sit at the LHC, which is great, you can go very high up, you clearly make a quark gluon plasma, and you sit at basically 0 baryon chemical potential. At top RHIC energies, you're also way up into the quark gluon plasma regime. But with our beam energy scan, where we vary the collisions at energy, we hopefully move around in the baryon chemical potential in the phase space with the goal, as you heard in the first talk, of discovering the critical point of the QCD phase space. So we have the beam energy scan, and we also have a novel program that was starting and is continuing in the so-called beam energy scan 2, which is now underway, collecting very high statistics, hopefully in this region of interest. We also turned RHIC into a fixed target experiment. And how we did that was we have a gold target that we place right at the entrance of STAR's TPC, so at a very high Z, and then you collide just one of the beams. So you take one of the beams, lower it down, so it just clips this gold target, which is right at the bottom of the beam axis. And then you turn RHIC from a collider into a fixed target experiment, which allows us to extend way down in square root S and cover the center of mass rapidity, and also go to large eta, because now we were basically a forward measuring detector. You can see here a collision at 4 GeV and how forward focused it is, to explore down at the very low energies, and as was again discussed in the first talk, look into the process of baryon stopping at these very low energies and potentially drop below the energy where a quark gluon plasma is made. What's very nice about this program is that we can collide at 7.7 GeV, and we can do this both at collider energies, so the top beam energy gets you to 7.7 in fixed target, and the lowest energy at which we can circulate beams successfully and have sufficient luminosity also gives us 7.7. So we have a way to sort of bridge between the fixed target and the collider by making measurements at the same beam energy. So that program has started, and here you see our first results at 4.5 GeV. And here you see HBT measurements. So what we're doing here is essentially measuring the size of the source at freeze out. And you see it here, it goes nicely. It goes from being oblate to being prolate as you go up in square root S. And the 4.5 GeV has a nice part of sitting basically at the transition from being oblate to being prolate, which is where you're heading from being baryon stopping dominated into sort of the quark gluon plasma high expansion regime. Another thing that's interesting about this is if you take ratios of the source size, so the so-called the radius on the out direction to the side direction, so the two transverse regions, and plot the ratio of this, this is predicted to have a non-monoticity as you go through a quark gluon plasma into the formation of the QGP through a first order phase transition. And with this new precision data that we have just taken, you see that indeed this appears to be exactly what is happening. with the transition happening around 20 GeV, giving us one of our many hints that we have from the beam energy scan 1, that we do pass close to this critical point at the lower beam energies. Another result that has recently come out from our initial beam energy scan, here you see as a function of square root S, with the lowest square root S in the top left, going up in square root S to 40 GeV, the nuclear modification factor for strange particles. And you see this separation of baryons and mesons that is occurring. Here you see the K star and the phi separated from the lambda and the psi. But as you drop down in energy, you see that this separation of baryons and mesons disappears. So there's some suggestion that the recombination is going away. And you also see that the turnover to jet quenching, which is apparent at the very high energies, and as you just heard from Andrea, is very extreme at the LHC, goes away as you drop down in square root S. Again, if I look at the baryon to meson, so here I'm looking at the strange baryon, the lambda that contains one strange quark, and the K0 short, the meson that contains one strange quark, you also see that there's a change in the behavior as you drop down from the highest energies here at 40 GeV down to our lowest beam energy scan 1 energy, of the splitting and the peaking of the baryon to meson ratio as you change centrality. So this is the most central collisions, has the highest ratio. And again, this is taken as a sign of recombination and the enhancement of baryons over mesons at certain PT, and that this is going away as you drop down in square root AS. Again, with the transition appearing to be somewhere around 20 GeV. And so the evidence for the critical point, there's some hint that we're changing from being quark gluon plasma dominated to hadron 1, and you have the experts in the audience who know much more about this than I do. Here you see looking for the critical point at it in all phase changes, you see the correlation lengths diverge. And so if you look instead at moments of conserved quantities, in the case of heavy ion collisions, one of the ones we have access to is the baryon number, the net baryon number, which we get at by looking at the net proton number, so looking at the difference of protons minus antiprotons. So, and if you look at this behavior of the moments, here it's the kurtosis times the variance, you should see a non-monotonic behavior, and this is evidence for the critical point. And this is what we're looking at here. So this is the kurtosis times the variance as a function of the beam energy from 200 down to our lowest energies. And you see in the open squares that we have basically just a monotonic dependence. It's very flat. It's no evidence of a critical point. But if you go up to the most central data, you see this bump structure, this non-monotonicity with about a 3 sigma significance. And so all of these effects and many other measurements that we're talking about have led us to ask for the beam energy scan 2, as it's called, which is a very high statistics running that's underway. It's a 3-year program. We're just about to start in 2021, the last year, and collect the last bit of data for it at both the collider and fixed target mode, in the effort to turn these hints where there are large error bars of 3 sigma significance is good, but it's not clear evidence yet of it, and try and beat down all of these error bars and come up with a definitive measurement for this. And as I say, that's underway at STAR with new detectors to have enhanced forward acceptance, better tracking and PID down to lower momentum, and try and come up with a definitive statement about where or if the critical point exists. You also heard from Andrea that initial conditions are complex at heavy ion collisions. When we first started 20 years ago, a lot of the modeling was done in a very uniform sense. And so you've heard about the V2, the elliptic flow. If you have only slight overlap of the gold nuclei, you get this elliptic mode. We then learned that, of course, the initial conditions are important and you have fluctuations in the density. So it becomes a more complex system. But these spatial anisotropies are still turned into momentum anisotropies. And then, of course, we discovered a few years later that you don't just have this elliptical mode because of the initial conditions and where the hot spots are in the system. You also end up with a triangular flow, a V3, a V4, a V5, as these complicated shape parameters transfer from the initial spatial into the momentum anisotropy that we can extract. And we quantify these by these so-called Vn, where n gives you the The 2 is the elliptic, 3 is triangular, and so on. But we've recently discovered that it's even more complicated than that. All of these anisotropy measurements focus on the transverse plane. But what about the longitudinal plane? If you look along the z-axis of the collision, this is generally assumed to be a uniform expansion. But of course, there are fluctuations along that direction as well. And that led us to look into these so-called longitudinal decorrelations, where you extract the Vn at positive and negative values of the z-axis or the rapidity axis and compare them, and you see whether there are twists along the beam line of the shapes of it. And that's what you see here. As you increase the rapidity of the measurement relative to the beam axis, you see that there is a significant decorrelation, and that the decorrelation here in red squares is for 27 GeV, 200 is the blue squares, and here you see the LHC measurements at 5 and 2 TeV. And you see that there is some decorrelation of the V2. But if you go to the V3 decorrelation, this becomes very large, up to 30% as you go out in rapidity at the lowest beam energies at RHIC that have so far been measured. So we have very strong evidence that we can't just assume a boost invariant of the expansion along the z or along the rapidity axis, that we actually have twists or so on of the shape of the fluid as you expand along the z-axis. And this is very important to our understanding to be including in the modeling. So talking of collective motion, what about looking into the charm? Do we thermalize the charm? And you heard from Andrea just now that this seems to be clear evidence that there is at the LHC, but what about at RHIC, where the temperature is lower and maybe the lifetime is shorter? So with the detector that we recently had installed, it's now been taken out, was a high precision silicon detector that allowed you to do the secondary verticing of the short lifetime of charm particles. And here you see the measurements on the right here of the D0, so the charm meson in gold-gold collisions as a function of centrality. And as you heard explained, you have the radial expansion, and you can, by fitting so-called blast waves models to this, you can extract the temperature and the expansion velocity. And here you see a comparison of those extracted for the pi kp, the light quarks, the strange quarks, and now the new data coming out from the D. And it's clear that the D0 is collectively flowing, but it appears that it decouples earlier from the medium than do the light quarks. It has a higher temperature, suggesting earlier, and smaller radial flow. But is there thermalization? And we get at that by looking into the elliptic flow parameter. And here you see the D0 elliptic flow. And there's clearly evidence of very strong collective flow for the D0. It's very similar to that of the light quarks, suggesting that the D0 thermalizes along with the light quarks, that it really does re-interact sufficiently that you have thermalization of charm quarks. And more recently, here you see preliminary results from Phoenix and START for the extraction of the elliptic flow of the bottom quark. You do this by looking at the so-called non-photonic electrons. B quarks, hadrons, often decay into something that leaves you with a high momentum electron. And because of the mass of the particles, the electron carries along a lot of the flow signature that of the initial B. And as you see, both at Phoenix and at STAR are in agreement that there is a non-zero flow of bottom. And at STAR, this is more than a 3 sigma effect from the statistics. So it seems that even the bottom quarks are beginning to show signs of thermalization at top RHIC energies. So what about the coalescence? You heard this again nicely, that they form, you have a quark gluon plasma, you have free quarks and gluons, and these, as they coalesce into hadrons, coalesce, pick up the flow of the quarks, and then those quarks turn into baryons or mesons by coalescing 2 or 3 quarks. For the mesons is 2, the baryons is 3. And the HFT, this high precision silicon detector, has allowed us to extract for the first time a charmed baryon, the so-called lambda C. So we can look at the baryon to meson ratio, as I just showed you for the beam energy scan with strange quarks, now in the charm quark regime. And so you compare it here, we compare it to the lambda to K, so the baryon to meson strangeness, and the P to pi for just light up and down quarks. And you see that you get very consistent measurements for all three of these ratios as a function of the centrality. So the more participants is the more fully overlapping it is. And that it's significantly above the measurements that are predicted by Pythia. So we have very strong evidence of coalescence of at least the charm quarks in our heavy ion collisions. Carrying on with how are the quark medium interactions going, we measure also the nuclear modification factor. Again, the solid circle is the D. And you see, as you go to high PT, you see a strong suppression, the energy loss. And it seems to be comparable to this in the open symbols of the light quark energy loss. So the D is interacting in a very similar way, suggesting that the charm is interacting in a very similar way, and that they lose a lot of energy traversing the QGP. And as I showed you for the elliptic flow, we also have now extraction of the charm nuclear modification factor and the bottom nuclear modification factor via access to the non-photonic electrons. And in green, here's the result for the charm. In the solid circles is for the sum of the two, which allows us, with knowledge of what the charm is doing, to get to the B RAA, or nuclear modification factor. And we see that there is an energy loss of the B, but we see that there's an energy loss systematic from it, that the energy loss of the B is less than that of the charm, which is similar to that of the energy loss of the light quarks and gluons. And this, as Andrea mentioned, is predicted to be because of the dead cone effect, that the gluon radiation, which is how we understand that partons passing through the colored medium are losing energy, are restricted as you go to higher and higher quark masses. What about looking into this quenching as a function of the medium size? So we've looked at it and it changes as a function of square root S. But it seems here, and this is again another measurement from Phoenix, preliminary, looking at gold-gold and uranium-uranium collisions here on the left. And you see that there seems to be a consistent energy loss, whether you measure it in uranium or in gold-gold, as long as you ask for the same number of participants. So the suppression is dependent on the number of participants, not so much on what particle species you're colliding. And if you come over here and look on the right, you see the results for the gold-gold, copper-copper, and copper-gold. And again, you see the same story, that it's what number of participants you measure that matters, not what system you're colliding. And we also see here, so we have it for pi zeros, eta, and k zeros, that if you're sat at the same number of participants, it doesn't matter if you're measuring strange or non-strange mesons, the energy loss appears to be consistent, which goes along with what I was just saying, that we have a clear energy loss and that there is a mass ordering only once you get to the high masses of the charm and bottom. So what about jets? We've been looking at single hadrons. If the energy loss is via gluon radiation, what about if we look inside of a cone here with a radius r, that's what we mean by a jet, and cluster all the energy together? Can we go back? Because in the end, energy and momentum has to be conserved. So can we get to a jet radius where we gather in that lost energy and be able to see what the initial parton had? And here you see the first full jet measurements in gold-gold collisions at RHIC energies. And you see that the energy loss remains when we expand this cone angle from 0.2 to 0.3 to 0.4. So the energy loss is really going out to very large angles. And we don't yet manage to cluster it back in, even with a cone radius around 0.4. So where does that energy go? How can we start to get it back? And Phoenix have been looking into this by looking at direct photon-hadron correlations. So you use the photon to be my jet trigger to give me the direction, and you look on the away side and look at the correlations of particles as a function of angle. And you see here, plotted as a function of this psi, which is a bit of a complicated variable, but basically you can think of this end is where the low momentum particles emerge, and this end is where the high momentum particles emerge. And here you see the jet quenching, and this is for 3 different photon tagged jet energies. You see the suppression at high momentum of the correlated particles. This is the energy loss going out. But as I go down and lower in hadron PT of the cone radius and looking at the low momentum, you see that you start to see the enhancement, which is the radiated gluons you're starting to gather back in. And if you look at this clear modification of the fragmentation function, a suppression of high momentum and an enhancement of low momentum, they decided to have a look at this and say, how large a cone angle do I have to go into to try and gather it all back? And you see here in red is for slightly small cone radius, and you see again the suppression at high momentum. But as I go out and make larger and larger, up to sort of basically looking in the other hemisphere, you're still gathering more and more of the particles back. So the enhancement of this gathering the energy back in, you really have to go out to very large angles before you gather all the lost energy back in, and which is an indication that there really is a rescattering of these gluons in the medium even after they're radiated, and they're sent out to very broad angles. And if we go down in collision species, looking into copper gold, and here is another full jet measurement with a cone of 0.2, you see here in the red, this is the most central data, that there's still a strong quenching even in copper gold collisions. And as I go down to more and more peripheral, by the time I'm at about 40% centrality, 60% centrality, you no longer have any energy loss. We're starting to go down into these small systems, into the place where either the QGP is not formed or it doesn't live long enough to have a strong quenching effect. What you also see is in this rather busy plot here in the open circles is the measurement for single pi zeros. And you see that the cone of 0.2 and the pi zeros, when you get to the same momentum, have a similar energy loss. It will be really interesting to have a look at larger radii and try and see if in this smaller system where the energy loss is smaller, do we actually manage to gather it back in? Can we find a cone radius where we gather in all of the lost energy? Because if we can gather in the energy by summing it all up, we can then look at the substructure and try and understand and learn more about exactly how the energy is lost. Another way we're looking at this is, well, the nuclear modification, this RAA, which is a ratio of the difference of the gold spectrum to the PP spectrum, depends not just on the energy loss, but also on the steepness of the spectra, on the spectral shape. So you could have, in effect, the same energy loss, but if the spectra are steeper, you get a more dramatic RAA. So another way to look at it is to look at the fractional momentum loss. So look at where do you have to shift the PP to get to the gold-gold? How much energy do you have to move it by, or momentum, to arrive at the same yield after scaling? And that's the so-called delta PT. And that's what we've done here for a variety of different jet measurements at star. And what you see is that the energy loss appears to be somewhere between 2 and 4 GeV is induced radiation into the medium, with some slight hint, although the data is not quite there, that the energy loss is getting smaller as you go to larger cone radii. Although, as I said, the error bars are large, but it's clearly there's somewhere around 2 GeV of energy loss. If you do a similar study at the LHC for Alice, you see that there's a much larger energy loss, as you would expect for this hotter, denser medium that is being created there. So onto the quarkonia, you heard about the dissociation. We're measuring the upsilon 1s to the epsilon 2 and 3s, and you see that there is a larger suppression of the upsilon 2s, so you have a consistent melting scheme that Andrea was talking about. The more loosely bound are easily dissolved in the hot medium, and you lose the suppression of them. But what you see is that the suppression is actually larger for these at star than it is for at the LHC, that's written here by the blue symbols, the squares, and that's because of the regeneration. You just don't have enough of the heavy quarks made at RHIC that they get melted and they can't regenerate. Whereas at the LHC, as again you heard in the previous talk, there's so much charm around that regeneration occurs, and so you quench them and then you reform them at the hadronization stage. But there is too few at RHIC, and so all we're seeing is the effect of the sequential melting at the beginning. On to other unusual things. As I get to the end of my talk, I'm nearly done. What else are we learning about this? We're still learning many new things at even after 20 years. And one is that the QGP is spinning, especially if you have peripheral collisions. You clip them and you put in an orbital angular momentum. And this you can extract by measuring the hyperon polarization. And you see that, again, measuring these through our beam energy scan as a function of square root S. And you see a very strong polarization for both the lambda and the anti-lambda. And we're getting here, we have the new measurements at 27 GeV and at 200 GeV. There are also now measurements at Alice that are consistent with 0, but we're getting to finite ones. And here you see the 200 GeV, that there is polarization, even though it's small. And one thing we're hoping to get out of our beam energy scan data is to look at the difference of the polarization between the lambda and the anti-lambda. So that there is a polarization tells you that it's highly vortical, it's walling with an amazing orbital angular momentum. But if you look at the difference between the lambda versus the anti-lambda, this gives us a handle on the initial magnetic field. There must be a magnetic field that's very strong because you have accelerated charges that are colliding. And hopefully this will help us get to it, which is one of the key important initial conditions, is exactly what is the initial B field and how does it decay away? Once you have a collective motion and orbital angular momentum, you might keep or sustain the B field for longer than just one would naturally think. So this is an ongoing program that has just started as we made these first polarization measurements, looking into the initial conditions. Another bit that you may not think about it be happening in heavy ion collisions is because we have so many stopped quarks there and such a baryon density, you can look at the creation of hypernuclei. And here we're looking at the hypertriton. So looking into the potential differences between the strange quarks and anti-strange quarks. Now, naively, one doesn't expect there to be any matter-antimatter binding differences in the strange quark regime, but one has to look. We don't want to just be naive. And this is the first measurement by STAR, indeed saying that there is no mass difference between the hypernucleus containing quarks versus that containing antiquarks with the strange one, but it's the first time this measurement has been made. And it allowed us to also get at the binding energy of the lambda, which differs quite widely from what the theoretical predictions are, assuming that there's a d lambda bound system. And this helps us put constraints on the hyperneutron-nucleon interactions and could potentially have some implications for neutron star modeling and where strange matter is predicted to exist. So these are sort of a handle that we have from having so many baryons around. It's a sort of an unexpected measurement out of the heavy ion. And the last one is our new one, looking at these light by light scattering. So this is when you look, yes, I've got like 2 slides to go and then I'm done. So we look at this, and so this is when you look at collisions that are so peripheral, the nuclei don't actually collide, it's just the 2 light quanta. And we're seeing evidence of the Bright-Wheeler process. Because you have this very strong magnetic field that I was just talking about, as you scatter them and have light scattering, you get polarization of the light that gives us this distinctive cos2 phi modulation or cos4 phi modulation by vacuum birefringent. So this is interesting. This is the first time it's been measured on the land. You sometimes can measure this as lights passing through pulsars. But with the very high strong field, you get linearly polarized photons. And as they pass through the magnetic field, as the angle changes, you get sort of basically a change in the refractive index. And we have measurements that are very consistent with this. So again, we've got to have this strong magnetic field. So it's given us another way to look into what is the initial magnetic field in these collisions. So in my last 2 seconds, there's still lots more to come. We have the STAR forward upgrades, which give us first time access to the very high rapidity, so very, very forward measurements. And that is going to give us a start looking into the physics measurements of the electron ion collider, which I'm sure many of you have heard about, just got approved by the DOE and will be constructed at Brookhaven, hopefully coming online in 2030. And so STAR is making these forward measurements to have a look more at the cold QCD, but there's many interesting heavy ion measurements as well, looking into the 3-dimensional part of the parton dynamics. And we expect to take first data early next year. And then also very exciting is S-Phoenix is almost here. So Phoenix was decommissioned and taken out of its hall to build the new S-Phoenix detector, which is designed to make the highest precision jet and quarkonia measurements that will be possible at the RHIC, to give us an enhanced understanding of the quark gluon plasma at all different length scales, and looking into at what point do the partons that we know are liberated in there and are point-like objects start to behave like the structureless perfect liquid that our fluid measurements, our VN measurements make. And this one is underway. It's being constructed as I speak, with an expectation to take first data in fiscal year 23. So it's 2 years out now. STAR will also be running at that point, and so we'll have access again to a whole new regime of very high precision jet and quarkonia measurements, again disentangling the details of how the medium interacts and what its properties are. Thank you.
Thank you, Helen. So the floor is open to questions. Let's take questions first for Helen, and then we'll go on to open questions. Yes, Rajiv.
Hi, did I get it right that at the STAR you do not see a cone R dependence for your R, the suppression, unlike at LHC?
Yeah, admittedly we have very large error bars, but there's not a dramatic. You could say there's maybe a hint that you're starting to gather it back in, but not really. You're right. It seems to be that the energy loss goes out beyond an R of 0.4.
But exactly the same values when you use of R, when you use on the, I think Atlas data it is, you see rather dramatic variations.
Yes, I think so. I mean, one has to watch a little bit what the momentum scales are. So exactly what energy you're expecting. So we know that the jet goes out to quite large angles at these jet momenta, even in PP. So I think we have basically one high momentum particle that you catch, and then you really need to go out to larger angles to gather in significant energy from it. So
okay.
Yes, there is a slightly different trend with R. But again, I think one should be careful to note, A, this is a log scale, and B, what are the systematic errors on this? But you don't gather in, you're correct in concluding at RHIC that so far we don't see evidence that there's a strong regathering of the energy out to a cone of 0.4.
Thank you.
Right. Next question, Rohini.
Okay, I hope we can hear me.
Yes.
Okay, Helen, thank you very much for a very nice talk. I'm going to ask a slightly out of the scope question. I mean, you mentioned what future holds for STAR and etc. What about the spin program? What are the outlook for that? Is there going to be any spin program or no?
Very good question. Yes, I mean, our forward upgrades are really driven program. So this is putting things at high rapidity. And so the first data next year will be next year now, I guess, we'll call it 22 next year, jumped across a few days, is going to be polarized proton collisions at 500 GeV. So really pushing into the spin program and continuing along that line.
Oh yeah, I noticed just now, universality of 3D parton dynamics. I should have, right. I missed that line. Okay, thank you.
It went very quick, but that's what it is.
I just missed that line. Thank you very much.
And of course, in the S-Phoenix era, it's dedicated to the heavy ion, but from 23 through 25, there will also be polarized PP collisions because RHIC can polarize protons, so why not? So we'll be taking data then at 200 GeV. And then there's also currently a plan for P-gold collisions to take place. S-Phoenix wants to take gold, P-gold, and PP, assuming it only runs for 3, they hope to run for longer, but they're definitely going to collect those data in. And again, that will be polarized P on gold as part of the cold QCD program, which leads into the EIC. Because that's why we're going forward, gets us down to the very low X range.
Thank you. Thank you very much.
To the EIC.
Thank you very much.
There's a question from Showman next.
Yeah, in your slide 11 on the B workflow, it looked like there was a very asymmetric error bar from STAR. What was causing that? yeah, this shaded region, a very large shaded region in the V2 of
I believe
B2E.
it's the corrections for the plane are, you basically, for the non-flow correction, you correct it only in one direction. The non-flow adds V2, but it doesn't subtract V2 into the measurement, if that makes sense to you.
Okay.
So you can make it with respect to an event plane, and then you have other things like jet physics will give you an apparent elliptic flow. If you just have a die-jet, that's the most extreme elliptic flow you can get. So you have a way to make your elliptic flow bigger by adding non-flow, but you don't make the elliptic flow measurement, the V2 measurement, smaller. So the correction only goes more or less one direction, the systematic.
Okay. Okay, but if you include that error, then your effect is not greater than 3 sigma.
If you take them all together, you have
No, for the B,
I mean,
for the B quark.
for the B.
Because you have the statement that
Yes.
it's
So I mean, if you
observed
look
for
here,
greater than 3 sigma, but with that shaded error,
so
it
this
doesn't look like it.
Right, out at the large PT, but down at these ones, this is consistent with being non-zero.
Okay, yeah. Thanks.
There's a question from
just on the
Ajit.
edge.
Yeah, hi. Yeah, my question is about this non-central collision. There is indeed very large angular momentum. What is not clear is how much of that angular momentum transfers to actual rotation. I would expect that when you go from very high energy to low energy collisions, the transfer will be more effective. So I don't know how one can.
Yes. And so that's part of why you expect to see the polar, I'm waving with my pen, that's not helping. Why you expect to see the polarization rise as a function of square root s, which is what we do see, is partly that the transfer gets larger. But at some point you expect it to go away. And here you see the Hardy's measurement, which, okay, has very large errors because you do also need the magnetic field to make this. Sure. And so at some point, if you don't make the quark gluon plasma to allow this to happen, you should end up back down at zero. So it should sort of rise steadily and then at some point go away.
Okay.
Because it's also the lifetime of, it gets very complicated because the B field, you have stronger B fields at the LHC because it's a higher momentum, but it's how quickly they decay away because also the ions head down the beam pipe. So it's quite a complicated mixture of how you transport it, what is the initial B field, how long does the B field last, at what point is the vorticity and the fluid there too. You need the fluid to have vortical moments. So there's quite some complexity in that measurement.
So you're saying this curve actually shows the transfer of angular momentum to rotation. This is how it has to be interpreted, is it? Towards the lower center of mass energy? Okay, great. Okay. Like that. Thank you.
Let me thank all the speakers first, and then open up questions to any speaker.
Let me stop sharing my screen so we can see the speakers.
Yeah. I think Rohini wanted to ask a question earlier to Andrea.
Yeah, thank you, Saurendu. Andrea, I wanted to ask you as to, you talked about the top quark physics studies. So I wanted to know what exactly one is, what physics one is going to be able to study with that top quark studies. Is it the energy transfer of heavy objects with media or interaction with media or what? Can people hear me now?
Yes, I can hear you.
Yeah, no, sorry, I was muted. So
okay.
it is essentially two things. One is to use the top quarks to probe nuclear modification of PDFs at very large Q square. So this gives constraints that you cannot reach with W and Z. So this is one thing. And the other thing is this time evolution of the medium density.
Okay.
So the situation is the following. You have a chain decay, you have a top going to W, and then the W goes to jets. Now, if the top is large momentum, then the W is boosted. And then the two quarks QQ bar pair from the W is formed after a few femtometers. So they start to interact with the QGP, not at the beginning, but after a few femtometers. So by looking at the jet quenching of these specific jets, you can study the jet quenching effect not at the beginning of the medium evolution, but after a few femtometers. So you study the time dependence of the medium opacity.
Okay, thank you.
It's very challenging measurements, but this is essentially the only way to access this kind of physics.
These will be pretty boosted tops, right?
Yes, yes.
So,
they have to have at least half TV, transverse momentum, which also means that you need a large, very large integrated luminosity to assess them. So at the LHC, one may have a first glimpse, but the physics case was actually constructed more for the future colliders.
Yeah, I understood that, but thanks very much. Thank you.
Okay, Rajiv has a question.
Again, my question is also to Andrea. I was a little puzzled by your flow of nuclei. In your plot, the one I had asked question was on the left, and on the right you had a plot. You showed A equal to 2 and A equal to 3 also flowing and showing a mass ordering. Is that right? Hello?
Yeah, Andrea, we cannot hear you.
Hello?
Hello, can you hear me now?
Yeah.
Yes.
Oh, sorry, I forgot. I was looking for the slide and forgot to unmute. So we see it for deuteron helium-3, and this supports a scenario in which these nuclei are produced by coalescence of nucleons that are produced in the system and then expanding in a common flow field.
Yeah,
So
that is exactly my worry. On the one hand, we are supposed to be seeing the quark-gluon plasma perfect fluid through this flow, and then you are going to have in that these heavy nuclei floating around, or what is the idea?
Well, yeah, this is what we are trying to understand. It is actually quite a puzzle why such nuclei can actually be observed and not destroyed by the interactions with the particles. But the idea could be that these are formed quite late in the system after the expansion and freeze out of the quark-gluon plasma, and they are formed by coalescence of protons and nucleons in the late phase of the system expansion.
So they flow, but that flow has nothing to do with the medium, which is perfectly fluid.
Well, it has to do with that, but it is not directly imparted to these objects, but it is inherited from the protons and neutrons that constitute them.
The energy scales are about factor of 2 orders of magnitude smaller.
Excuse
the
me?
nuclear binding is of the order of few MeV.
Yes.
And the coalescence that might take of quarks and gluons to form protons or pions is of the order of few hundred MeV.
Yeah. Yes. Yes. This is still let's say an unresolved puzzle. How these objects can remain bound and still they seem to participate in the expansion of the system.
Can I ask
And
right.
to understand it better, we also plan to make measurements with A=4 nuclei in run 3, and of course also measuring the yields and not only the elliptic flow.
Okay, so Rajiv, I think the ball is in the theorist's court at this point. So let's go on to the next question, which is Shauman.
I was a little puzzled by this energy loss in small systems probe that Andrea talked about. So if you are trying to see whether you see QGP-like effects in smaller systems, isn't the R parameter the wrong thing to look at? You showed an R ratio and said that that doesn't change in P-laid kind of system. But shouldn't you look at something which does not have a ratio with PP?
Yes, we have also done that. This was done by Alice, looking at hadron jet recoil measurements. So we take a trigger hadron with high PT, and then we look at the energy of jets recoiling from this trigger hadron, and we compare P-led high multiplicity and P-led low multiplicity collisions. And at the moment, we also don't see an evidence for an energy shift in this type of measurement. So this one doesn't require a ratio and any assumption on the geometry of the P-led collision.
Okay. Just on a similar vein, I mean, what about a ratio like epsilon 2s by epsilon 1s? Do you look at that and multiplicity dependence of that?
Yes, there are measurements by CMS, by the CMS experiment of that, and there is an indication that epsilon 2s is reduced with respect to epsilon 1s when you go to high multiplicity, and this is also seen for the psi 2s with respect to the J psi. However, the interpretation of these measurements is far from being simple, and actually models can describe the measurement with in terms of breakup of these states in interactions with hadronic comovers like pions. So it is not straightforward to associate these measurements to a possible suppression due to color screening.
Thank you very much.
Okay, I think Sayantan wants to ask a question, but after that, I want to ask Sayantan a question.
Yeah, should I go ahead?
Yeah, this.
Okay, I had a question for Helen. So you mentioned about the fixed target program at RHIC. So what are the main observables you're planning to look at? I remember that RHIC had some results for the eta and eta prime mesons and their decay. And here, of course, the multiplicity will be more, I guess. So is it, are you planning to look at those mesons?
Yeah, so we should have enough statistics to do sort of all of the light quark measurements, so measuring spectra and yields of light hadrons and strange ones. We probably won't be able to do anything at the charm and above level. We don't have enough statistics, or to get to very high PT. So there's be an attempt to do some start of looking into RAA, but that's unlikely to get to sufficiently high momentum. But hypernuclei are underway, all the different resonance measurements that you can make with light particle invariant mass are being studied. Because we have quite nice coverage. We got the TPC was upgraded, so it has a larger rapidity acceptance and goes down to lower PT. So our total momentum coverage is much better. And we also have a forward time of flight, or at least it's forward in the fixed target one. So we can do PID much better out there as well. So we expect to sort of have the whole slew of resonance measurements done at the end. And hopefully even some of these kurtosis measurements.
Thanks.
At least the higher low energy measurements.
Okay. Rajiv has a question, but before
Thanks.
that,
And could I ask another question too?
Sure. Go ahead, Sayantan.
Helen, I also had a question regarding your this electron pair production. So it is, if I understand correctly, it is not the Schwinger pair production, but just the birefringence that you are studying, right?
Say again? Sorry, I didn't quite get that.
So for the slides that you showed about this electron pair production, you're looking at the vacuum birefringence. So this electric field is not strong to use the Schwinger pair production, right? Or is it?
That's right, yeah. So you assume that it's a light by light scattering of the fields as the nuclei pass close but don't actually physically interact. And then you have the high magnetic field.
And what is the typical magnitude of the electric fields there?
The magnetic fields are many tens of Tesla.
Sorry, the electric field.
I don't know. That's a good question. I don't know what the magnitude of the E field is.
It should be strong enough, but I don't think it's so strong to produce pairs, right?
I think that's correct. That it's getting high, but it's not expected to be the dominant source of production. It's not that high. This is really pairs coming from photons.
Okay.
Yeah,
thanks for the very nice
talk. And ask a question to Helen about the jet angle. It strikes me that the opening angle of the jet could depend upon the path length that you have traversed through the medium. So I wonder whether there's some correlation with some other signal, not the jet on one end, but some other thing at the other end, which you could correlate to find, to bin in different path lengths and then look at the opening angle, because otherwise you're kind of trying to impose the same opening angle for jets which pass through different amounts of matter.
Yeah, that's a very good point. And that is exactly what we are trying to do. So we found a way that seems to be slightly better just because of the medium size and the amount of lost energy to swing the amount the recoil jet passes through the medium on average by asking for the leading particle on the away side to have differing amounts of energy. And you can imagine if we really ask, because it's such a steeply falling spectrum at RHIC, if you ask for there to be two very high momentum back to back, then they must be basically tangentially produced and haven't passed through the QGP. And as you reduce the restriction of the momentum on one, you swing yourself more and more into the quark gluon plasma. And we have some evidence that that works in previous publications, that if we look at this R of 0.4 and require some significant momentum on the other side, you can see that you do gather the energy back depending on where you put the low momentum threshold. So we seem to be able to swing into the medium. And the most path length through, which is why photon jet measurements are very interesting, or the W and Z, if you can get to these, is that they don't interact with the medium because they're colorless. So that gives you sort of, hopefully sort of the unbiased one. They come out of the center because the photon can travel without energy loss. And so we do have a way, and we're calling it jet tomography is the buzzword for it, that are just starting to be done and also occurring at the LHC, comparing photon jet to jet measurements in an attempt to change the path length, or even to go to slightly more peripheral where we still see an energy loss, but we know the shape is elliptic. And then you can look at the jet loss as a function of the angle to the reaction plane. And you can imagine you pass through either the long or the short length of the elliptic medium and have the same medium but different path lengths and try and see. I mean, those are very statistics hungry measurements. And I would say at the moment there's hints that we can see a path length dependence, but it's not a very strong evidence yet, mostly because our error bars are pretty large still.
Thanks.
That's part of the goal of the S-Phoenix to be able to do, that they can collect really high statistics and do jet measurements. The calorimetry is all there, including hadronic calorimetry and good tracking to try and do these sort of high precision measurements.
Can I also ask the same question to Andrea? Would Alice be able to track path length and energy loss or opening angle?
Yes, this is something that we have been looking into in Alice. I'm not sure about the other, about Atlas and CMS. For Alice, it seems we will need to wait for the statistics of run 3 to make such a multi-differential measurement. So from the run 2, it seems that we are limited by the integrated luminosity. But certainly it is something that is under the radar for run 3.
Thanks. So this is just statistics limited at present for both experiments.
Yeah.
Okay, thanks. Now Rajiv has a question.
Yeah, this one is at Sayantan. You said that the P6 dip is related to UA1. Can you say why?
Yeah.
And how come for a staggered quark?
Oh, that was...
that which doesn't have UA1, you see a dip?
Yeah, so the results are in the continuum limit. So we would expect that in the continuum limit, the UA1 should be restored.
No,
and
you will not
that
do that.
it
No, you
may
will not
be...
do that. You will not do that. You continuum limit, UA1 will not be restored. Remember, that is...
No, restored meaning the exact symmetries of the staggered.
No. The other symmetries, yes, but UA1, no.
Agree. This looks like it needs more explanation.
Yeah, and this I'm not so sure about, but regarding your question that why it's related to UA1 was studied in a model, sigma model with this toothed interaction. That was a work by Rob and his collaborators. So they studied different fluctuations and in such models, and then they tried to see whether these are these quark meson models with this UA1 type of interactions included in it.
I see.
And so depending on the strength of this UA1 interaction, they can see this negative slope. And of course, it is a non-perturbative. It is very clear because the the calculations from perturbation theory, like in the resum perturbation theory, there always the sixth order baryon number fluctuation goes positive and then falls to zero at large, at higher temperatures.
Okay. Thank you.
So perturbation theory cannot get this negative dip just above TC.
Okay. Thanks.
So Rendu, can I ask one question to Sayantan? I cannot raise hand because of co-hosts.
Right.
So Sayantan, this is regarding ruling out
Yes.
a critical point in the phase diagram. You had two numbers. One is
Yeah.
temperature below 135. So my question
Yeah.
is there some uncertainties on those numbers? Second is you had also a limit on the mu b by T greater than 2.5, but that was in a temperature range.
Yeah.
So can you please little bit tell us?
Yeah. Yeah. So the temperature range, the temperature below 135 MeV comes from the argument that all the higher order fluctuations should be positive. Now the eighth order fluctuation is only still the errors are large, but it seems that it is only consistent with zero below this temperature. Above this temperature, it goes to negative values. And that is also clear from the trend from the sixth order baryon number fluctuation. So if one looks at the sixth order baryon number fluctuation plots, then if one takes the temperature derivative, that is equivalent to going to eighth order fluctuation, and that should go to negative values just above TC, just above 135 MeV, around that. So
135
yeah.
plus minus 10 MeV, 20 MeV, or 5 MeV?
It should be lower than 135. Yeah,
Yes.
135 or lower. Yeah.
So that's already taking the systematics into account. 135.
No, we have not taken any systematics here because it will. Nothing is. This is just a rough, bound here. So we are not predicting a number in that sense.
Okay. And
so it will depend on how precisely we measure the eighth order fluctuation. So if we have a better precision, then we can give a bound for that.
and the mu b bound is obtained only in narrow temperature range. Is there any reason?
Yeah, that is between this 135 to 140 MeV. So in that range, UV by T should be greater than 2.5.
I see. Okay, thank you.
Sayantan,
And this number is also not the final answer because we only take the results from the estimator up to sixth order baryon number fluctuations. So with higher orders, the numbers may change. That we have to look at.
Okay, thank you.
Sayantan, I have a question for you.
Yeah.
When you, in the first kind of 1/3 of your talk, you put together a lot of very nice reasoning to argue that there are non-PDG states which have to be taken into account if you want to use the hadron resonance gas to explain the lattice data. Okay. So you were,
Yeah.
the story I got out of that is that the PDG is not enough. Okay. There are these negative parity baryons. There are, their mass, their effects, temperature effects on mass. There are new strange particles and so on, which you must all put together. Is that right?
Yeah. Yeah. Yeah.
Okay. But then when you talk about curvature of the critical line, okay.
Yeah.
You said that the freeze out that you observe through fitting hadron resonance gas to experimental data agrees with the lattice, and you start from
Yeah.
that and you developed an argument. Isn't this kind of contradicting the first part of your talk? Shouldn't you not take, if the first part of your talk is to be taken seriously, then you should not take the hadron resonance gas fit to give you a freeze-out temperature, shouldn't you?
Sorry, I rushed through that part. So recently, there was a recent analysis of the Alice results by the group from Andronic et al. And so previously, as you know, that for the Alice results, the statistical hadronization model and this thermal fits could describe all the particle multiplicities very well except proton, which was off by 15%. So recently they have looked at doing the same analysis, taking into account this quark model states, and then those quark model states, they decay into the lighter baryons, and they took into account all of these systematics. And what they found out is that things become worse due to this delta star and n star resonances. So then they took into account the pion-nucleon interactions through S matrix, and they concluded that when one takes into account those interactions, then again the freeze-out temperature comes to be around 156 MeV, which is around what lattice results done. So the main conclusion is they need quark model states, but few of the states they may be non-resonant. So it's important to take into account this repulsive interaction. And when one takes into account these facts, then the temperature that comes out is consistent with the lattice results.
Is this the same paper as
for the RHIC energies? I'm not so.
Is this the same paper that argues that the extra strange states are not cannot be accommodated?
No, this is the paper that came out last month.
Okay, so the one before the
new
paper
analysis,
that says,
including the quark model states.
So that's the one before the one that states that the extra strange states that you are talking about cannot be accommodated.
The strangeness I didn't see in their paper, but at least
I think that's a later
with the light baryons, yeah.
Okay. Okay, there's a question by Nihar.
Hi, Santan. It was a very nice overview talk. I have a question on your slide 18. I need some explanation. How do you get that conclusion that thermalization observed for 19.6 above 19.6 GeV? Because one of your slide and many lattice people also say that lattice and hadron resonance gas model breaks out at 154 or 156 MeV. So how that thing and this thing is compatible? That's my one question. And second question is, and how do you, so out of these three mean and higher order moments and combined fit, which one we should consider? That's my question.
So regarding your statement,
Yes.
So regarding a question, indeed, so even with the Alice results, when one takes into account quark model states and these corrections of the pion-nucleon interactions, one sees that the temperature, freeze-out temperature that one gets, is consistent with the lattice results. For the RHIC, of course, one has to take into account the decays from these resonances, and whether one then the issue is whether these resonances are within the rapidity bin that you're measuring. So that's why it's important to look at different observables, and that's why in this they looked at observables that depend on this pion kaon scattering correlation divided by the variance of the net kaon and such observables. So those are not so much sensitive to this resonance decays. So from there one concludes that of course there was a joint fit done with just only the mean values for the particle multiplicities, and also with all these new observables which are usually second order. They also considered the skewness for net proton kaon and the ratios of skewness by the appropriate numbers. And then with that joint fit, it seemed that the temperature and the chemical potentials that come out from all these fits are consistent with each other. So just taking the mean, whatever temperature and the chemical potential you get, you also get the same, including these higher moments in the analysis. And that is true for these square root S higher than 19.6 GeV.
Thank you.
So,
Yes, Nihar.
Yeah, did I answer your question or?
Yeah, I was
Yeah,
looking for a little bit different, but we can discuss offline in another forum. Thank you.
Okay then.
Yeah,
So
sure. Okay.
I think I'll end the session now because we've already extended this session by about 35 minutes. So I would like to end by thanking everyone, the three speakers, Sayantan, Andrea, and Helen. Thank you very much for this nice talk and for staying on to answer questions for such a long time.
Thanks to you.
Thank you. I'll also like to thank the audience, so many of whom stayed on to ask questions, to listen to the discussion. So thank you everybody for participating, and we end the session now.
Thanks, Sorendu. Thank Andrea, Helen, and Sayantan. Thank you very much.
Thanks, Vedant.
That was a great
Thanks
discussion.
very much
Thanks
to
for
you.
staying up, everyone. Yep.
Thank you.
Bye-bye.
Good
Thank
night.
you.
Bye.